For this operation, we're going to be using an STM32 Nucleo board, as well as a breadboard with an LCD screen. The first program that's going to be used is going to be doing an 8-bit operation to be able to output this display on the board. As you can go see, we have the wiring for this. You have the STM Nucleo board, and you have the LCD module. For this, we have corresponding outputs. They're going to be the main outputs of PC0 corresponding to DB0 through DB7. Additionally, we're going to have pin 15, which is hooked up to 5 volts, 220 ohm resistor into pin 15, which is going to be LED plus. Then LED minus is going to be pin 16, which is going to go straight to ground. Up at the top, pin 1 is going to be fed directly to ground. Pin 3 is going to be fed to a 5 volt source. And pin 2, which is V0, is going to be on a 10K potentiometer to allow for a contrast control. For this program, we're going to be using something fairly simple. It's going to be using a flowchart, which is going to have the actual LCD display main program. It's going to define a few of these initial values. It's going to load the initialization of the LCD, the delay function, the actual data that's going into the LCD, as well as individual ports that are being put in. For this one, it's going to output the text 8-bit hello and an 8-bit method. It's going to delay for 1 second, clear it, wait another half a second, and then it's going to repeat the operation. As you can see in here, that's what it's doing. It's displaying hello for 1 second, and that's going to clear for half a second, and rinse and repeat. For all these additional dip switches that you see, this is used for the third operation. For this code right here, you can see this is going to be the LCD display. This is going to be using the main pins of PC0 through PC7, corresponding directly with pin D0 through D7 on the LCD board. So for this one, we're going to have one main while loop, which is going to be pulling information from multiple void loops from outside the main. But the actual text that's going to be displayed is right here, which is going to say hello in an 8-bit method, delay for 1 second. It's going to clear it, and then it's going to wait another half a second, and then rinse and repeat. For this one of the biggest challenges was to incorporate the delay function previously used using a assisted clock. And then it's going to be pulling individual data from all these individual void functions right here. We go on to the next one, which is going to be the same setup. This is going to be using a 4-bit operation as well. The same exact wiring, the same exact grounding, and everything. For this one, the flowchart is pretty similar to the last one, but for the instead, we're not going to be using the RW on this. We're not going to be defining that function. Going through the same exact method, except we're going to be outputting capital hello with the 4-bit just to be able to signify the difference between the 8-bit and the 4-bit methods. Delaying for 1 full second, clearing the LCD, and then rinse repeating for another set of cycle for 500 milliseconds. For the wire of this one, let me just pull it up. We have fairly the same code. We're going to be using the assisted clock again, as well as for this one, we're operating from PC4 through PC7. In the actual write-up for this, we explained that we have the wiring still continued for the 8-bit operation, and we have the additional unused pins of PC0 through PC3. For this one, we're just using PC4 through PC7. For this one, we're not using the RW function. We're still enabling a lot of the same void functions. And then we go into the main loop, which is going to output the text of hello in capital followed by 4-bit. It's going to delay for 1 second and then clear it, delay for 1 full second, and then rinse and repeat. For the same thing, one of the biggest challenges for this was to be able to convert some of the values over from 8-bit to 4-bit. For what we did here was we shifted the bits left 4 additional bits, as well as masked the unused bits. This was just specifically for the output of GPIOC. And we use the same systolic clock for the actual delay function. Pretty similar what we did for the character display for the void LCD data loop as well as the command. And we have an additional function, LCD nibble port. Lastly, we have this function right here, which is going to be a LCD BCD converter, which is going to be defining the RS, RW, and the EN values for enabling. It's going to initialize the LCD delay, the LCD data, as well as the ports, all in the main function or outside the main function. Then it's going to, within the main, it's going to define and initialize the GPIOC pull-up resistors. Those are going to be used for the input pins for C8 through C11, which is going to be pulling from the IDR. From that, it's going to read the BCD input, and then it's going to output the corresponding decimal value from a lookup table, and it's going to output that on the display. It's going to wait 2 seconds. It's going to clear the LCD and then rinse and repeat. I'll show all 3 programs at the end here. So for this one, we're going to be using the LCD input. For this one, it's pretty simple compared to what we're using. We decided to use the 8-bit method rather than the 4-bit method. We still enabled and defined the same functions with the addition of initializing the GPIOC internal pull-up resistors as well as the input data registers. For this one, we're going to be taking a value which is going to be input off of PC8 through PC11, which is going to be the 4-bit number, and it's going to use that value and apply it to this lookup table right here. From this, it's going to take this lookup table and it's going to output it on the LCD display. From there, it's going to delay 2 seconds, it's going to clear it, and then rinse and repeat. And this can use the same functions, void functions from the previous 8-bit operation. So for this, right now we have the LCD display loaded for the 4-bit operation. It's already loaded onto the board. And you can see it is outputting the hello in 8-bit and lowercase. We can go to this one, we'll remove it. And then we'll load up the LCD 4-bit. So from here, we're gonna build the 4-bit one. We're gonna load it, have no errors. Go back to the board, we're gonna reset it. And now we have hello in capitals followed by 4-bit text. We'll come back over here. We're gonna remove this file. And then we're going to be loading up the LCD BCD input. From here we'll run it, load it, and we'll come over to the board, we'll reset it. Currently we have all 4 of our switches in the 0 position, so it's 0, 0, 0, 0, which is going to output on the lookup table A0. You flip up the first one, which is going to give us a 1 after 2 seconds. It'll display a 1. Then you can try this with 3. You put up another one, you'll get 7. Put up another one, you should get F. And then we could try this also for the even numbers as well. So I flip them all down. You could try just the second switch, it gives you 2. Individually, you could try number 4 by itself. Give it a second to reset. And then you could try 6, which is middle 2. And then 8, which is far left one by itself. We'll reset this back down, and you can see the 10 kilo ohm potentiometer, which that individually will adjust your contrast and brightness for the LCD bits. Improves, as I said, these additional pins. These are our main pins 1 through 16, and we're going to be mainly using the D0 through D7 pins for the 8-bit operation, and for the 4-bit operation we're going to be using D4 through D7. And then for the 8-bit one, we're using all these pins with the addition of the 4-position dip switch.